Einstein published his equations in 1915 during the First World War, but he couldn't find an exact solution. Luckily, a copy of his paper made its way to the Eastern Front, where Germany was fighting Russia. Stationed there was one of the best astrophysicists of the time, Karl Schwarzschild. Despite being 41 years old, he had volunteered to calculate artillery trajectories for the German army.
At least until a greater challenge caught his attention: how to solve Einstein's field equations.
Schwarzschild did the standard physicist thing and imagined the simplest possible scenario: an eternal static universe with nothing in it except a single spherically symmetric point mass. This mass was electrically neutral and not rotating. Since this was the only feature of his universe, he measured everything using spherical coordinates relative to the center of this mass. So r is the radius, and theta and phi give the angles. For his time coordinate, he chose time as being measured by someone far away from the mass, where spacetime is essentially flat. Using this approach, Schwarzschild found the first non-trivial solution to Einstein's equations, which nowadays we write like this. This Schwarzschild metric describes how spacetime curves outside of the mass. It's pretty simple and makes intuitive sense. Far away from the mass, spacetime is nearly flat, but as you get closer and closer to it, spacetime becomes more and more curved, it attracts objects in, and time runs slower. Schwarzschild sent his solution to Einstein, concluding with, "The war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Einstein replied, "I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution to the problem in such a simple way." But what seemed at first quite simple soon became more complicated. Shortly after Schwarzschild's solution was published, people noticed two problem spots. At the center of the mass, at r equals 0, this term is divided by 0, so it blows up to infinity, and therefore this equation breaks down and it can no longer describe what's physically happening. This is what's called a singularity. Maybe that point could be excused because it's in the middle of the mass, but there's another problem spot outside of it. At a special distance from the center, known as the Schwarzschild radius, this term blows up. So there is a second singularity. What is going on here? Well, at the Schwarzschild radius, the spacetime curvature becomes so steep that the escape velocity, the speed that anything would need to leave there, is the speed of light. And that would mean that inside the Schwarzschild radius, nothing, not even light, would be able to escape. So you'd have this dark object that swallows up matter and light. A black hole, if you will.
But most scientists doubted that such an object could exist because it would require a lot of mass to collapse down into a tiny space.
How could that possibly ever happen? Astronomers at the time were studying what happens at the end of a star's life. During its lifetime, the inward force of gravity is balanced by the outward radiation pressure created by the energy released through nuclear fusion. But when the fuel runs out, the radiation pressure drops, so gravity pulls all the star material inwards. But how far? Most astronomers believed some physical process would hold it up. And in 1926, Ralph Fowler came up with a possible mechanism. Pauli's exclusion principle states that fermions, like electrons, cannot occupy the same state. So as matter gets pushed closer and closer together, the electrons each occupy their own tiny volumes. But Heisenberg's uncertainty principle says that you can't know the position and momentum of a particle with absolute certainty. So as the particles become more and more constrained in space, the uncertainty in their momentum, and hence their velocity, must go up. So the more a star is compressed, the faster electrons will wiggle around, and that creates an outward pressure. This electron degeneracy pressure would prevent the star from collapsing completely. Instead, it would form a white dwarf with a density much higher than a normal star. And remarkably enough, astronomers had observed stars that fit this description. One of them was Sirius B. But the relief from this discovery was short-lived. 4 years later, 19-year-old Subrahmanyan Chandrasekhar traveled by boat to England to study with Fowler and Arthur Eddington, one of the most revered scientists of the time. During his voyage, Chandrasekhar realized that electron degeneracy pressure has its limits. Electrons can wiggle faster and faster, but only up to the speed of light. That means this effect can only support stars up to a certain mass, the Chandrasekhar limit. Beyond this, Chandrasekhar believed not even electron degeneracy pressure could prevent a star from collapsing. But Eddington was not impressed. He publicly blasted Chandrasekhar, saying, "There should be a law of nature to prevent a star from behaving in this absurd way."
And indeed, scientists did discover a way that stars heavier than the Chandrasekhar limit could support themselves.
When a star collapses beyond a white dwarf, electrons and protons fuse together to form neutrinos and neutrons. These neutrons are also fermions, but with nearly 2,000 times the mass of an electron, their degeneracy pressure is even stronger. So this is what holds up neutron stars.
There was this conviction among scientists that even if we didn't know the mechanism, something would prevent a star from collapsing into a single point and forming a black hole. Because black holes were just too preposterous to be real.
The big blow to this belief came in the late 1930s, when J. Robert Oppenheimer and George Volkoff found that neutron stars also have a maximum mass. Shortly after, Oppenheimer and Hartland Snyder showed that for the heaviest stars, there is nothing left to save them when their fuel runs out. They wrote, "This contraction will continue indefinitely."
The black hole's gravity is warping the fabric of space. Everything that travels through this curved space must follow a curved path, including light.
Space stuff is awesome. Take stars, 100 billion megaton per second thermonuclear explosions that just don't stop exploding. Pulsars, city-sized atoms that beam death rays through the galaxy. Giant molecular clouds, beautiful and tranquil, but also screaming vortices spitting stars into the cosmos. Of course, everyone knows that quasars are the most awesome of all. They have everything. They don't just have a black hole, they have a supermassive black hole, millions to billions of times the mass of the Sun. That's surrounded by a solar system-sized whirlpool of superheated plasma that shines brighter than an entire galaxy. Sometimes they even have jets of near light speed particles filling the surrounding universe with giant radio plumes. Yep, quasars are clearly the most metal of all the space things. This is one reason why I study them myself, but it's not just that they're cool. Quasars helped shape our universe. In fact, without these most violent of all astrophysical phenomena, we might not be here to think about them.
The closer to the supermassive black hole we travel, the more dangerous it gets.
As we approach the central core of M87, we start to feel it. But all this energy, all this ferociousness is powered by that black hole.
Intense winds start to buffet the ship. They push away vital gas, quenching star birth.
We will be looking at some sort of random angle to the accretion disk. We may be even looking edge on. And in that case, do we see this shadow of the black hole? You might think that we wouldn't. But the truth is, because of the way the black hole warps space-time and bends light rays, we actually see the back of the accretion disk. The way it works is light rays coming off the accretion disk bend over the top and end up coming to our telescopes. So what we end up seeing is something that looks like that. Similarly, light from the bottom of the accretion disk comes underneath, gets bent underneath the black hole, and comes towards us like that. And this is where we get an image that looks something like the interstellar black hole.
This discovery is about the collision of two neutron stars. These neutron stars were orbiting each other, approaching the speed of light, and then they collided. They produced a burst of gravitational waves. And then what is really extraordinary is that this burst of gravitational waves is followed by a gamma ray flash, and then a flash of light, then a slowly revealing burst of radio waves. This has ushered in a new era in astronomy called multi-messenger astronomy. This is a first for the world, where we've had 1,000 scientists around the world working on this problem, and now we can understand how the universe is really working. We can understand the very early universe, the first fraction of a second when the universe formed. We can now understand the most exotic creation of stars in the universe. This also leads to the evolution of life, because life requires certain elements that are created from the stars. For the first time, scientists have identified exactly where and exactly how far away this explosion happened. This one, we know exactly that it is 120 million light years away in another galaxy, a very exotic galaxy. Using the Zadko telescope, international collaborators in France and also in Australia work together to capture the light, and this will allow us to unlock a very mysterious process of metals forming after the neutron stars collided. The gold that you are wearing, a fraction of that gold has come from the collision of neutron stars. The data produced is so rich and so extraordinary that it will keep scientists working for years trying to understand that data and combine it in new ways. There will be hundreds of scientific publications announcing new discoveries following this event.
From Earth, the night sky shines with a multitude of bright speckles. For the most part, these are stars, huge balls of plasma infusion that radiate intense light due to their high temperature. Although they twinkle slightly due to disturbances in the atmosphere, the brightness of stars is fairly stable. But in the 1960s, observing the sky in other wavelengths, astronomers discovered bright spots that flicker over time. These points seem to emit extremely regular oscillations. Their luminosity pulses in a metronomic way. We call them pulsars. To understand where these pulsars come from, we will have to immerse ourselves in the life of a star. We are interested in a star 10 times more massive than our Sun. During its lifetime, the star burns its fuel in a process of nuclear fusion. The core of the star releases energy outwards, which allows it to counterbalance the pressure of gravity and thus remain stable. But at the end of its existence, after 100 million years, our star is exhausted. It has run out of fuel and the nuclear fusion in its core stops. The star is no longer in equilibrium. Nothing opposes the pull of gravity and the core begins to collapse under its weight. As it shrinks, the star's core compresses. Its temperature rises to several billion degrees and it begins to spin faster and faster, generating an increasingly powerful magnetic field. After a while, the core becomes so dense that the particles that make up matter are forced to merge. Electrons enter the nuclei of atoms and combine with protons. They form neutrons and in the process reject a tremendous amount of neutrinos. Suddenly, the core becomes so small that neutrons collide with each other. At this point, the core can no longer shrink. The contraction stops abruptly and the outer layers of the star are violently blown away by the shockwave and the wind of neutrinos. The star explodes. It's a supernova. The supernova explosion leaves behind a gigantic remnant, a cloud of interstellar gas and dust which may one day give birth to new stars. But after its death, the core of the star has not vanished. It is still there, but it is now a tiny ball of matter, formed of neutrons stacked together. This is a type of stellar corpse, called a neutron star. When they form, neutron stars can occur in different configurations. Many stars, for example, orbit in pairs, in binary systems, around another star. After the death of one of them, the neutron star it leaves behind can sometimes continue to revolve around its partner. Similarly, if the star was initially surrounded by planets, these will sometimes continue orbiting the corpse. A neutron star is an incredibly dense object, which contains the mass of several suns in a few dozens of kilometers. This is the equivalent of the mass of Pluto squeezed to fit inside a house. If it were compressed even slightly more, gravity would take over and it would turn into a black hole. The neutron star is also extremely hot. In some cases, surface temperature can exceed several million degrees. Due to its small size, it spins extremely quickly. While it shrinked, the core that formed the neutron star accelerated until reaching near light speed velocities. A neutron star can rotate almost 1,000 times on itself in just a second. A car with wheels turning this fast would move at 7,000 kilometers per hour. On the surface of a neutron star, gravity is unbearable and gives rise to strange phenomena from relativity. First of all, time is greatly dilated. If astronauts landed on the neutron star, they would only age 10 months for each year that passes on Earth. Unfortunately for them, the tidal forces are also insufferable. The difference of pull between their head and their feet is here 100 million times stronger than Earth's gravity. They would instantly get spaghettified. Finally, the neutron star deflects light rays around it, bending the geometry of space-time. Like a black hole, it creates a gravitational lensing effect, distorting the image of surrounding objects, and even allowing us to observe its rear. The internal structure of a neutron star is still poorly understood. Small and very distant, it is impossible to observe their composition from Earth. We have to rely on mathematical models and quantum physics to describe how matter compresses. At the surface, a neutron star is most likely surrounded by a thin atmosphere, no thicker than a human hair, under which lies a perfectly smooth surface as the strong gravity flattens any roughness that would protrude. Under its surface, the neutron star has a crust, mainly solid, made up of atomic nuclei and free electrons. As we dive deeper, the pressure increases, and the nuclei begin to combine with the electrons to form neutrons. The high pressure helps stabilize these heavy nuclei, which would normally decay very quickly. Deeper and deeper, the nuclei combine with each other and merge to form even larger clusters. The more we dive into the crust, the more the competition between gravity, electromagnetism, and the strong interaction forces these clumps of matter to merge together. Further down, the nuclei form long structures in the shape of tubes. Deeper still, these tubes are forced against each other and merge to form a pile of layers stacked on top of one another. Finally, these layers fuse together, and the spaces gradually close, leaving only a few bubbles in a liquid of neutrons. These different structures that make up geometric networks inside the crust would constitute one of the strongest materials in the universe, a sort of large-scale atomic nucleus which researchers called nuclear pasta. Their geometry is indeed reminiscent of gnocchi, spaghetti, or lasagna, names that scientists use to classify them intuitively. If we decide to dive even deeper, we venture beyond the limits of the crust and enter the core of the neutron star, where the pressure is greatest. The core of a neutron star is an extremely difficult region to describe. It reaches the current limits of our models. The pressure is so intense that the principles of quantum physics come into play. In particular, the particles are so close together that they repel each other by the simple fact that they mustn't overlap. This is called the exclusion principle. The form of matter whose structure is governed by the exclusion principle is called degenerate matter. Degenerate matter is still mysterious, and there are several different hypotheses about its structure. It could simply be neutrons stacked together. But neutrons are not elementary particles. They are themselves made up of quarks, and one could imagine that under such pressures, the quarks would separate to form a superfluid, or even a plasma of quarks and gluons, whose properties would be exotic. The insides of a neutron star still remain an enigma, which researchers are actively trying to solve. During its formation, the neutron star acquired an extremely powerful magnetic field. On Earth, scientists are able to generate magnetic fields of several dozens of Tesla, enough to levitate objects and even living beings. But a neutron star generates a magnetic field that is several million times stronger. Such a magnetic field is so intense that it can even alter the vacuum itself. It provides space with weird quantum refraction properties. Light moving by may be deflected, split, or recombined. Just like a magnet, the magnetic field of a neutron star exits through a north pole, wraps around the star, and enters it through a south pole. The neutron star therefore has a magnetic axis, which in most cases is not aligned with its axis of rotation. When it spins, the magnetic field of the neutron star follows this rotation, creating intense fluctuations which propagate at the speed of light. Reasonably close, the magnetic field of the neutron star traps the surrounding matter and forces it to stay near the star. Conversely, at a great distance, the magnetic field varies so quickly that it opens and accelerates charged particles outwards. In this way, the neutron star produces two beams of extremely powerful electromagnetic waves that escape along its magnetic axis. Like a cosmic lighthouse, these radiation beams sweep space periodically and emit a signal whose oscillations pulse metronomically. When Earth is in the way, we observe a tiny bright spot which flickers in the sky. It is a pulsar.
To recap, when the Sun ages, it undergoes a series of changes in its core. It's fusing hydrogen into helium now, today, and will eventually fuse helium into carbon, and it'll make a dash of oxygen and neon too. But when it runs out of helium to fuse, it's in trouble. It doesn't have enough mass to squeeze the carbon nuclei together, so they can't fuse. Fusion is the Sun's energy source. Once the core is nearly pure carbon, that power is switched off. By this time, nearly 8 billion years from now, the Sun's outer layers are gone, expelled by all the shenanigans going on in the core. What's left of our star is just its core, exposed to the dark of space. Over the next few billion years, it'll cool and fade to black. That might seem like the end of the story, but I skipped a step, and it's a beauty. When helium fusion stops, the Sun's core will have about half the mass of what the Sun does today. The rest will have blown away into space around it. What remains is basically composed of electrons and carbon nuclei mixed with a small amount of a few other elements. So what kind of an object are we left with here? You may know that light charges repel. Electrons have a negative charge and repel each other. The tighter you squeeze them, the stronger that pressure. There's also a second force called electron degeneracy pressure. It's a result of some of the weird rules of quantum mechanics. For you QM nerds, it's the Pauli exclusion principle. This describes how subatomic particles behave on teeny scales. One of these rules is that electrons really hate to be squeezed together, above and beyond simple electric repulsion. This resistance is phenomenally strong and becomes the dominant force in supporting the core of a star once helium fusion stops. By the time this electron degeneracy pressure balances the core's immense gravity, the core is only about the size of Earth. 1% the original width of the Sun, and it's called a white dwarf. Listing its characteristics is enough to melt your brain. Ironically, everything about it gets amplified as its size shrinks. It becomes ridiculously dense. A single cubic centimeter of it, the size of a six-sided die, has a mass of 1,000,000 grams, 1 metric ton. An ice cream scoop of white dwarf material outweighs 60 cars. Because it's so dense, the gravity at the surface of a white dwarf screams up, easily topping 100,000 times the Earth's gravity. If you have a mass of 75 kilos, you'd weigh 7,500 tons if you stood on the surface of a white dwarf. Not that you can. Stand there, I mean. You'd be flattened into a greasy smear. But not for long. Newborn white dwarfs are hot. They can glow at temperatures of upwards of 100,000 degrees Celsius. If you were on the surface, you'd be a vaporized and ionized smear. Their intense heat makes them white, and they're small, hence their name. They're so hot, they also glow in the ultraviolet, even in X-rays. Weirdly though, because they're so small, they're actually quite faint. The closest one to us, Sirius B, can only be seen with a telescope even though it's 9 light-years away, one of the 10 closest known stars. Over 10,000 white dwarfs have now been found in our galaxy. Still, any gas near a newly formed white dwarf is likely to be affected by the intense radiation pouring out of it. And hey, wait a sec. When a star like the Sun is in its final death throes, it expels its outer layers as a gaseous wind. You don't suppose? Yep. By the time that white dwarf forms, the gas blown off hasn't gotten very far from it, at most a light-year or two. That's plenty close enough to get zapped by the white dwarf radiation, causing that gas to glow in response.
All that remains, a glowing white dwarf, the leftover core of the dead star. But in galaxy GSN 069, the supermassive black hole turbocharged the process. It stripped off the outer layers of the red giant in a matter of days.
The black hole has almost eaten all the juicy parts, all the easy-to-get-at parts of the star.